In this example, we're told that the market price in dollars of used cars of a certain model is found to be $1,000 plus 2 cents per mile times X, where X is the distance in miles west of Detroit, and then it decreases by $2 per day multiplied by T, where T is the time in days. So the longer you own the car, the lower its price is. That's pretty typical depreciation as time goes on. And then here, the price of the car actually increases the further you get from Detroit. Maybe that's supply and demand. Lots of cars are located in Detroit, and once you get further away, they're harder to come by, so the price goes up. Anyway, we're told that if the car of this model is driven from Detroit at t equals 0 toward the west at a rate of 400 miles per day, so this is telling us how fast we're leaving Detroit headed west, determine whether the value of the car is increasing or decreasing, and how much of this change is due to depreciation and how much is due to moving into a better market. So let's go ahead and figure this out. This is actually a Lagrangian derivative kind of problem because we're trying to find how the price changes with respect to time because, of course, it's changing with time, but also because we're changing our position with time. So this will be the Lagrangian derivative of the price, and that's comprised of this Eulerian component of the derivative. So this is our Eulerian or local part of the derivative, plus the convective portion, which will look like this. So this is the convective part. And I'm only doing it in the x direction. That's not convection, it's convective. And that's only in the x direction just because we're just moving west. We're not worried about moving in 3 dimensions or 2 dimensions or anything like that. So let's find the depreciation component. The depreciation component is the Eulerian part. It's how it's changing with respect to time. So the price goes down by $2 per day here. So when I take the derivative dp dt, that's just going to be a minus $2 per day. And then now let's do the convective component here. Here, the u is the velocity that we're headed west, and we're told here it's 400 miles per day. So 400 miles per day. Oh, let me divide through by day. Times dp dx, which is just how the price is changing as I change my position. So we go back up to here, and you can see it changes by 2 cents per mile when I take the derivative. So when you combine these together, what does that come out to be? That's something like $8 per day. So that's this component, and here's our depreciation. So when you add those two together, we're coming out $6 a head per day. So the price of this vehicle is actually going up per day by $6, and the reason is even though we have some depreciation that's decreasing the value, we're moving into a better market every day. So we're getting further and further west of Detroit, so our price goes up by $8 per day. So when you add them together, we're going up by $6 per day. So hopefully this makes sense. This really, I think, is a good illustration of how there are two components to the time derivative as you follow a fluid particle, or in this case, actually follow the car. You have a component due to how things change with time, known as the Eulerian component, and you have a component that's due to changes in position, which is called the convective component. So this really illustrates the difference between the depreciation or the changes with respect to time, as well as the convective component, which is due to changes in position. All right, we'll go ahead and end there.